Okay, let's unpack this. Think about your favorite piece of music. Maybe it's some soaring opera, or maybe that really deep bass line that just rattles your chest.
Yeah.
We feel it as, pure emotion, pure art.
Mm-hmm.
But hiding just underneath all that magic is?
Mm-hmm.
Well, it's physics, isn't it? Elegant, kind of unforgiving physics.
That's absolutely spot on. Everything you hear, really everything, a tiny whisper, a whole orchestra.
Right.
It's just a physical vibration, a pressure wave moving through the air.
And the journey that wave takes from being this, analog thing in the air
Yeah, this vibration.
to becoming tiny bits of digital data on a disk. That's what we're diving into today.
Exactly. It's quite a trip.
So our mission, if you will, is to decode the basic science. The stuff that defines every single sound.
We'll break down those 3 key qualities, the ones that let you tell a cello from a clarinet.
Pitch, intensity, quality.
Right. And then look at the clever math needed to capture it.
And finally, how things like CDs, DVDs, Blu-rays actually store something so huge in such a tiny space. These microscopic pits.
We could maybe start with a great example from the source material. The idea of superposition.
Okay, superposition.
Yeah, think about, say, an oboe and a clarinet playing the same note together.
Right.
Each one makes a sound wave, but the shape of that wave is unique, like a fingerprint for the instrument.
So different shapes of vibration.
Distinct shapes, exactly. Now, when those 2 waves are out there in the air at the same time...
They don't just, bounce off each other?
No, not at all. They physically combine. They superpose.
Yeah.
The peaks add up, the troughs add up, or cancel out. It creates this single, really complex new wave shape.
So they sort of mash together.
A perfect mashup, yeah. And that single tangled up wave, that's what actually hits your eardrum.
That's what we hear as harmony or just music.
Precisely. It's this physical collaboration.
Yeah.
But to record it, to reproduce it accurately,
We need to understand the building blocks first.
we have to get those 3 fundamental physical attributes down. The components.
Okay, let's jump into section 1 then. The 3 pillars of sound perception. First up, pitch.
Pitch. This one's pretty direct. It relates straight to the frequency of the wave.
Frequency meaning how fast it's vibrating.
Exactly. How many times the wave cycles up and down per second. We measure it in hertz, or hertz.
Right, so high frequency means lots of cycles per second.
Yep, fast cycling. And that's what our brain interprets as high, thin sounds, like a flute maybe.
And low frequency, slower cycles.
Much slower cycling. That gives you those deep, thick, low sounds. Think tuba or double bass.
Got it. And the range we can actually hear is pretty big, right?
Oh, it's vast. The data shows humans typically hear from about 20 hertz. That's a really low rumble, barely audible.
20 hertz.
All the way up to around 20,000 hertz. 20 kilohertz, which is quite high-pitched.
Okay, let's make that concrete. Say a cello plays middle C or do. What frequency is that?
Right, a do on a cello. That's vibrating at roughly 264 hertz.
So 264 times every second, the string and the body of the cello are pushing and pulling the air.
That's the physical event happening, yes.
Yeah.
A measurable vibration.
Okay, but here's where it gets weird for me. You mentioned that lowest note, 20 hertz.
Ah, yes, the wavelength. This is where intuition kind of breaks down.
Tell me about it. How big is that wave?
Well, that 20 hertz bass note, it's sound wave, physically, in the air. It has a wavelength of about 17 meters.
Wait, hang on, 17 meters? That's huge. That's like the length of a bus.
Out that, yeah, city bus, maybe even articulated.
You're telling me that deep rumble you feel at a concert isn't just the speaker cone moving a lot, it's an actual pressure wave stretching 17 meters across the room.
That is the physical reality of that sound wave in air. It's
Right.
massive.
Wow.
It really helps you grasp why low sounds can feel so, well, physical. There's large-scale movement involved.
Okay, my view of bass drums has officially changed, right?
Yeah.
Moving on. So that's the type of sound, the pitch. What about the energy, the loudness?
That's the second pillar. Intensity.
Mm-hmm.
We perceive it as loudness.
And that's driven by the wave's amplitude.
Correct. The amplitude is essentially the height of the wave, the magnitude of the vibration. More amplitude, more energy, more loudness.
And we measure that in decibels.
Decibels, yes. But there's a crucial point here. The decibel scale isn't linear. It's logarithmic.
Logarithmic, like the Richter scale for earthquakes.
Exactly like that. It's a really important comparison. A jump from, say, 40 dB to 50 dB isn't just a little bit louder.
It's 10 times the intensity.
10 times the energy, yes. So when you think about the range, a quiet whisper might be around 30 dB.
Okay.
A really loud concert could hit 100 dB, maybe more.
So the difference in actual physical energy between that whisper and the concert isn't just like 3 times. It's
astronomical. It's a huge, huge difference in power hitting your ear.
Millions of times more energy.
Immense, yes. Our ears are incredible devices to handle that range.
Yeah.
Generally, we talk about 0 dB being the sort of threshold of human hearing.
The quietest sound we can detect.
Right. And then maybe 120 dB is getting up towards the threshold of pain. You don't want to be there for long.
Definitely not. Okay, so pitch is frequency. Intensity is amplitude. What's the third one? The most maybe subtle one.
Yes. Quality, or as it's often called, timbre. Pronounced timbre.
Timbre, right.
Yeah.
And this is the magic ingredient.
It really is. This is what lets you hear a violin and a flute playing the exact same note, same pitch, same loudness, and instantly know which is which.
Even with your eyes closed.
Exactly. It's the instrument's unique sonic fingerprint beyond just the fundamental note.
So how does that work physically? What creates that difference?
It's all about complexity. Timbre is determined by the presence and the relative strength of extra frequencies called harmonics or overtones.
Harmonics. Okay. What are those?
They're additional waves that vibrate at whole number multiples of the main fundamental frequency.
So if the main note, the fundamental, is 100 hertz.
Then the second harmonic is exactly 200 hertz.
Yeah.
The third is 300 hertz, fourth is 400 hertz, and so on. Intermultiples.
And different instruments produce different sets of these harmonics.
Precisely. And crucially, at different relative loudnesses, different intensities.
Ah, okay. So when that cellist plays the 264 hertz do.
They're not just creating 264 in twos, they're also simultaneously creating 528 hertz, 792 hertz, 1056 hertz, and so on.
Wow.
Each with its own specific volume. That particular mix, that recipe of harmonics, is the sound of the cello.
And a flute playing 264 hertz creates a different recipe of harmonics. Maybe fewer or maybe stronger, higher ones.
Exactly. A different blend, a different balance. That's timbre.
So if you could somehow filter out all those harmonics, what would be left?
You'd be left with what the source calls a pure sound, just the fundamental frequency.
What does that sound like?
It's typically a very simple, smooth sine wave shape. Think of like an old electronic keyboard tone, or tuning fork perhaps. It sounds quite plain, sterile almost.
Not very musical.
Not really. Music really lives in the richness, the complexity that those harmonics provide.
Okay, this is fascinating, but it brings up a huge question for me. If real musical sound is this incredibly complex thing...
This mashup wave.
Yeah, this mashup of the fundamental plus dozens, maybe hundreds of these harmonics happening all at once. That big, messy, maybe 17-meter long wave. How on earth does recording technology capture that? It feels like trying to, I don't know, perfectly recreate a gourmet meal just by smelling the air in the kitchen afterwards.
That's a great analogy. And it highlights exactly why we have to talk about the genius of Fourier Analysis.
Fourier.
The entire world of modern audio, from multi-million-dollar studios right down to the earbuds you might be using, it all rests on the mathematics worked out by Jean-Baptiste Joseph Fourier way back in the early 1800s.
And he wasn't even studying sound originally, was he? Wasn't it about heat flow or something?
That's the amazing part. Yes, he was analyzing how heat spreads through objects, but his mathematical discovery turned out to be incredibly universal.
What did he discover?
He proved, mathematically, that any complex, repeating wave, no matter how jagged or complicated it looks.
Like our combined oboe and clarinet wave.
Exactly. Or the pattern of heat across a metal plate. Any such wave can be perfectly broken down, decomposed, into a sum of simple sine waves.
Simple sine waves, like that pure sound you mentioned.
Precisely. A fundamental sine wave plus a specific set of harmonic sine waves, each with its own precise amplitude and frequency.
So, instead of trying to capture that one big, messy wave shape,
which would be incredibly difficult, maybe impossible to do perfectly,
we capture the recipe for the wave.
That's it, the exact recipe. We don't record the complex final wave, we record its ingredients, the fundamental frequency and the precise frequencies and amplitudes of all the harmonics that make it up.
The Fourier gave us a way to take the complex sound apart into simple pieces.
He gave us the mathematical tool to analyze the complexity, find the simple components, and list them out. That list, that recipe, that's what we can convert into digital data.
Wow. Without Fourier, high-fidelity recording just wouldn't exist as we know it.
It would be fundamentally impossible, I think. He provided the bridge from complex physical wave to manageable mathematical description. He turned the art in the air into organized math.
That mathematical organization, that's the perfect lead into section 2. We've got this recipe, this list of ingredients for the sound. But it's still an analog signal, right? A varying voltage, maybe?
Still analog at that point, yes. A continuous representation of the sound pressure.
So how do we take that, representing maybe a 17-meter vibration, and somehow squeeze it onto a shiny little plastic disc?
Now we have to cross the bridge from the smooth, continuous analog world into the blocky, discrete world of digital, zeros and ones.
And that means digital sampling.
Exactly. We have to measure the level, the amplitude of that analog sound wave thousands upon thousands of times every second. Take snapshots.
And the standard for the original compact disc, the CD, that set a pretty high benchmark for this, didn't it?
It really did. For CD audio quality, the standard sampling rate is 44,100 times per second.
44,100 measurements every single second. Why that specific number seems oddly precise.
It's not arbitrary at all. It comes from something called the Nyquist-Shannon sampling theorem. Basically, it says to accurately capture a wave,
You need to measure it often enough.
you need to sample it at least twice as fast as the highest frequency you want to reproduce.
Okay, and we said human hearing goes up to about 20,000 hertz.
Right. So double that is 40,000 hertz. Sampling at 44.1 kilohertz gives us little headroom and ensures we capture everything within the range of human hearing with high fidelity.
Got it. And all those samples, those numbers, end up stored on the CD, which holds about 700 megabytes, 0.7 gigabyte.
Roughly, yeah. 700 millibyte was standard for a music CD. And physically, how it stores it is quite clever.
It's the pits and lands, right?
Exactly. The data is encoded as a long spiral track of microscopic pits, tiny depressions burned into the surface, separated by flat areas called lands.
And a laser reads that.
A laser beam reflects off the disc. When it hits a land, it reflects back strongly. When it hits the bottom of a pit or the edge between a pit and a land, the reflection changes. It scatters or cancels out.
And the CD player detects that change in reflection.
And translates that pattern of changes back into the stream of ones and zeros representing the sampled audio.
Clever. But 700 millibeat, I mean, that was amazing for music, but for video, or even higher quality audio later on, it wasn't enough.
Not nearly enough. Storage density had to improve, which led us pretty quickly to the DVD, the digital versatile disc.
Right, DVDs, they looked similar but held way more data.
A lot more. A standard single-layer DVD holds about 4.7 gigabytes.
Whoa, that's like 7 times more than a CD.
Roughly. Yeah, a huge leap in capacity.
And how did they do that? Was it a totally different technology?
Fundamentally, no. It was still a plastic disc with pits and lands read by a laser. The breakthrough was primarily physical refinement, miniaturization.
Smaller pit.
Much smaller pits, packed closer together in a tighter spiral track. And, crucially, to read those smaller pits accurately.
You need a finer tool.
Exactly. DVDs use a laser with a shorter wavelength, typically red light, but shorter than the infrared laser used in CD players.
Like needing a sharper pencil to write smaller letters.
Perfect analogy. Shorter wavelength light can be focused to a smaller spot, allowing it to resolve finer details, those smaller pits.
Okay, so if the rule is shorter wavelength allows smaller pits, which means more data, I see where this is going.
You can guess the next step then.
Blu-ray.
Blu-ray disc. It continues exactly that trend.
And holds even more.
Significantly more. A single-layer Blu-ray disc holds about 25 gigabytes. Dual layer holds 50 gigabytes.
25 gigs, that's another massive jump from DVD.
It is, and the clue is right there in the name, Blu-ray.
It uses a blue laser.
Precisely. Blue light has an even shorter wavelength than the red light used in DVD players,
So it can focus down to an even tinier spot.
allowing it to accurately read even smaller pits packed even closer together.
Higher density storage. So the amount of music, or more likely high-definition video, we can fit on a disc is literally limited by the color, the wavelength of the laser light we can create and use reliably.
Fundamentally, yes. It's a direct consequence of the physics of light in optics. It's this constant push towards miniaturization, driven by the need to store more and more data without sacrificing the quality of the original signal.
The quality captured by that Fourier analysis way back at the start.
Exactly. We need the density so we don't have to compress the audio or video too much and lose detail.
So let's recap this whole journey. We started with sound as this, well, potentially enormous physical pressure wave in the air.
Up to 17 meters long for those deep bass notes, yeah.
We saw how even complex sounds are combinations of simpler waves, thanks to Fourier.
Allowing us to create that precise mathematical recipe.
Then we sampled that recipe thousands of times a second, turning it into digital ones and zeros.
44,100 times a second for CD quality.
And finally, we store that massive stream of digital information as incredibly tiny physical variations pits on a plastic disc.
Pits so small, We need short wavelength blue laser light just to read them accurately on a Blu-ray.
It really connects the macroscopic world of sound waves with the microscopic world of data storage.
It absolutely does. And if you step back and think about the bigger picture here, the sheer range of scale involved is just mind-boggling.
You mean the 17-meter wave versus the tiny pit?
Exactly.
Yeah.
You have sound waves spanning the length of a bus traveling through the air, and our ability to capture and reproduce that relies on manipulating light at the nanometer scale, the wavelength of blue light, to read features carved onto a disc that are measured in millionths of a meter.
Bridging huge physical phenomena with incredibly precise microtechnology, all just so we can listen to music faithfully.
It's quite something. And it makes you wonder, doesn't it? Kind of raises this interesting question for you, the listener, to think about.
What's that?
Well, what other really vast physical phenomena, things that happen on huge tangible scales in our world? Think about weather patterns, atmospheric pressure changes, maybe even geological shifts.
Big real-world stuff.
Yeah. What other massive scale things are we currently managing to measure, compress, and capture using similar kinds of microscopic digital precision right now? Our ability to map and digitize reality hinges on these breakthroughs, constantly pushing the boundaries between the very large and the very small.
That is a fascinating thought. Where else is this macro to micro translation happening? Great point to ponder.
Indeed.
Well, thank you for joining us on this deep dive into the secret physics hiding inside your music collection and your Blu-ray player.